Hello everyone, welcome to this video. In this video we shall be learning about the orders of group, orders of subgroup and the number of distinct cosets which a group may have, right? So here is this Lagrange's theorem, which is very important theorem. This theorem has been found more than 200 years ago, right? So here this theorem is in fact older than the group theory itself. So let's see what does this theorem actually tell us. It tells us that if G is some finite group and H is some subgroup of the group G, then the order of the subgroup H that divides the order of the group G, right? And moreover, the number of distinct left or right cosets of H in G that is given by the division of the order of the group G and the order of the subgroup H, right? So this is the result with us. Now let's move forward on to the proof of this theorem. For the proof is also very simple. In the proof we have A1H, A2H up to ARH as are different distinct cosets of the subgroup H in the group G, right? So now we have the count of distinct cosets as R. So we have this thing. We wanted to prove that this R is equal to the order of G divided by the order of H, right? Because R here denote the number of distinct cosets of H, and that is what we wanted to prove here in the second part. In the first part we wanted to prove that this H divides the order of the group G, correct? So for that, let's first consider distinct cosets of H in the group G. Then for each element G, now we have this group G over here. Now we select an arbitrary element A from this group G. For this particular element, now because you see, if you remember, we can divide whole of this G into distinct cosets, right? Each would have a equal size. So now this A would be present in some of the cosets. Suppose it is present in this coset. If you take any element from G, it would be present in any one of the cosets, right? So let me call that coset. Suppose that if I consider this A in G, so therefore the coset which is generated by this coset representative A is actually equal to AIH. It is one among these distinct cosets. Why? Because these are the only possible cosets that we have with us, right? So therefore, according to the properties of cosets that we have studied, we have the element A present in the coset AH. That is true. So therefore, we can say each member of the group G that belongs to one of the cosets AIH, because if you select any element from the group, it would definitely be a member of any one of the cosets. So that is what we are saying here mathematically. So in symbols, it would mean that we have divided this G into distinct members, right, which are nothing but the cosets of G. So therefore in this case we can write this G as the union of A1H, A2H up to ARH, right? So therefore again, using the properties of cosets, the above union that is disjoint in nature. Why? Because distinct cosets, they partition D completely into distinct cosets because they have nothing in common, and so therefore the order of each of these subgroups, that when we combine their orders, they would result in the order of the group G, right? So this is one thing here. Moreover, we have the order of each of the coset AIH is equal to order of the subgroup. Why this is so? Now, can you guess this thing? It is because if you remember in the previous example, we had the subgroup as 1, 15. So each of the subgroup is obtained by few numbers which are nothing but the same in order in number. So here we have two elements, so the next coset would also have two elements. Why it is so? Because we are just multiplying this coset representative which every member of this subgroup H. So that means the order here would going to be the same. So therefore the order of each coset here would be equal to the order of the subgroup here for each I. So that means this order G is it is now written as the order of H, the order of H, the order of H, and so on up to this order of H. So that means each of the order of different cosets could now be written as the order of subgroups. So that means, and how many of them are there in total? There are total R such orders, right? So therefore when you add the orders of H R times, it would be R into H, and this is what we wanted to prove. We wanted to prove R is equal to the order of G divided by the order of H. So what does it mean? It means that the distinct R represents the distinct cosets of H in G. So that means the number of distinct cosets of H in G is given by this expression, the order of G divided by the order of H. And moreover, from this expression we can clearly say that the order of H divides the order of G. Why? Because we do have zero remainder here, and according to the division algorithm, the order of H divides the order of G, and this is what we wanted to prove here in this theorem. So I hope you understood this theorem well. Well, that is it for this video. Thank you for watching.